Hello and welcome to another episode of the Science on the Edge podcast. I'm Dr. Mark Darcy, and in today's episode I'm going to be discussing memory. I'm going to talk about the different models of how we construct our memories. I'm discussing the pros and cons. I'm going to also talk about the neuroscience of memory, the biology basically of how we physically construct memories. I'll discuss the reasons why we forget. I'll talk about the phenomenon of false memories. I'll also touch upon how we might improve our memory. There are a number of different methods which do work really quite well to allow us to store and retrieve memories more efficiently. Okay, so let's get started. So first, a little definition is probably in order. So, phenomenon of memory. What is memory? So memory is any indication that that learning a particular task or a particular piece of information has persisted over time. So memory is basically our ability to store and retrieve information. Now, before I get started into the nitty-gritty of it, I just want to dispel a few myths relating to memory. So a survey was conducted, and here are the results. First of all, 83% of people surveyed believe that suffering from amnesia typically results in a failure to recall your own name or your identity. This is not true. This is a myth. Most people that suffer from amnesia still do recall their own identity. They might fail to recall new events, new information that's given to them, or they may have a block regarding a particular event or series of events in their life, but they tend to recall their personal identity. So that's one myth dispelled. 37% of people surveyed believe that the testimony of a confident eyewitness should be enough to convict a defendant of a crime. That's 37% of people. This is wrong. This is wrong. Eyewitness testimony is notoriously weak. It really is. We don't recall a lot of the information, a lot of the experiences that occur in our lives. And if you're in a very tense situation, you might be focusing on one very tight aspect of that event. So, for example, if someone is holding a gun up to you, then you'll probably remember very clearly everything about that gun. That's where your eyes will be fixated. But if you're later asked details about what the person was wearing, about other people in the room, even the face of the individual, you may not recall very clearly those events. So you do tend to get tunnel vision when you witness some sort of crime. And later, when interviewed by perhaps a police officer, you will fill in the gaps with best guesses, with your imagination. So eyewitness testimony is very, very fragile, and it should not be given the high status that it is by many people. Okay, so 63% of people interviewed believe that human memory works kind of like a video camera. It accurately records events and information that we are exposed to. It doesn't. It's not like a video camera at all. It really is not. We create our memories based on our feelings, our thoughts, our emotions, our imagination, and yes, sensory information around us. But it all comes together. It all comes together to create a memory which is a vague record of an event, but usually not very accurate. So another myth dispelled there. Okay, so 48% of people surveyed believe that once you've experienced an event and formed a memory from it, that memory remains unchanged over time. Again, this is incorrect. You may form a memory, and at the time that you form the memory, it might be very, very accurate or fairly accurate. But over time, the memory does begin to deteriorate. A memory is a very plastic structure. Think of it more like plasticine than clay. Every time you activate a memory, the plasticine becomes pliable and it changes its form ever so subtly. So if you think of a memory as kind of like an electronic circuit, you create a circuit by connecting a bunch of wires together. That's the initial memory. Now, when you try to recollect that memory, what you do is you take that circuit apart and reconstruct it. So think about it like this: you create a memory, so you create an electric circuit of kinds in your mind, in your brain, and then when you try to recollect that memory, the circuit becomes dynamic again. Wires are taken apart and put back together. They're mostly put back together in the same form that they were originally, but parts of the memory that you failed to recollect, so perhaps you're remembering a birthday party, you can remember roughly who was there, you can remember roughly the music that was playing, but not exactly. So what you do is you fill in the gaps. So perhaps there was another birthday party a few years before or afterwards, and you can remember quite clearly what people were wearing there or the music that was playing. You can't recall quite so clearly this particular birthday party. So what you do is you fill in the gaps in one memory with what you know from another memory, or what you assume. Perhaps your friend John, when you were 7, usually wore a particular jacket. So you assume that at that particular birthday party he had that jacket on. So what you're really doing when you reactivate the memory is you're adding to it, you're removing from it, you're reconstructing the circuit. And when you lay that circuit back down, it's now subtly different. And each time you reactivate a memory, this same process occurs. So over time, memories bend, they twist, they change, and over a few years, the memory that you think you recall very clearly could be very different than the original memory. So memories, they really are not that accurate. Okay, so 55% of people surveyed believed that hypnosis was useful when it comes to recalling events, to bringing back memories to the surface. So hypnosis in the past has been used quite a lot to try and retrieve lost memories. However, hypnosis is a very fickle technique. Hypnosis relies on suggestion. It relies on suggestion to get someone into an hypnotic state. The individual needs to listen to the hypnotherapist and to basically do as they're told. They become suggestible, they fall into a trance, and that state of suggestibility remains throughout the hypnotic session. So it really opens up the patient or the subject to the possibility of creating false memories. So if a hypnotherapist does not word his questions very, very clearly, very, very neutrally, then he runs the risk of placing false memories in the patient. And this has happened. I will talk about this later in the podcast, but a number of people have been arrested, convicted of crimes that they did not commit, based on evidence given by witnesses under hypnosis. False memories were implanted in the hypnotic subject's brains, and even the hypnotic subject believed these memories to be true, but later they've been proven not to be true. So hypnosis is not reliable. It can be useful, but it's all down to how the hypnotherapist conducts such interviews. So hypnosis, it doesn't necessarily bring up accurate memories. In fact, it can create false memories in the subject. 78% of people interviewed, surveyed, sorry, believe that when people notice something unexpected, so when something enters the field of view that was unexpected, they will pay attention to it. It will leave a memory. That's not true. That's not always true. Yes, usually if some unexpected event occurs, your attention is directed towards it and it will create an impression and perhaps a memory. But it all depends on what's going on inside your mind at the time. So, for example, if you're walking down a street and you're procrastinating, you're thinking about some event that occurred early on in the day or some future event, you can be completely unaware of your surroundings. This is how people get hit by trucks crossing the road. You know, the attention is just distracted by what's going on inside the mind, and suddenly they're in an accident. But it's more than that. There have been cases where people have been present when a crime has been committed and been completely unaware of that crime. For example, there was a rape that occurred in Central Park in New York a few years ago, and a jogger ran right past the incident, so right past, within a few feet of the rape. So the jogger was jogging through the park, a rape was occurring, he ran right past it, and he failed to report the crime. The police actually tracked down the jogger, and they arrested him. They arrested him for not reporting a crime. And long story short, this went to court. A few expert witnesses were brought in, some neuroscientists, and it was determined that it's quite possible, in fact very likely, that the jogger in question was so engrossed in his exercise. You know, he was jogging, he was trying to get a better time, he was focusing on his steps, he was focusing on his time, that he was oblivious to everything else around him. This can happen. This can happen. So just because something new and novel occurs around you does not mean that you notice it. So now it's time to start to talk about memory construction. So in the following 10 minutes, 20 minutes or so, I'm going to be discussing memory construction. Specifically, I'll talk about misinformation, imagination effects, amnesia, how to discern true and false memories, children's eyewitness recall, and repressed or constructed memories of abuse. So to start that process, I will talk a little bit more about the nature of memory. So memory is kind of like an internal record or representation of a prior event or experience. I kind of covered that in my initial definition. But to expand on that, memory is also a constructive process in which we actively organize and structure the information that we process, store, and retrieve. So, talking about storage and retaining information, memory can kind of be broken down into a number of different blocks. There is our sensory memory, working or short-term memory, the long-term memory, and then obviously more physically there is the mechanism by which we actually structure memories in our brains. So let's talk about the different models of memory. So there's 4 basic memory models. I'll describe them in turn. First of all is the information processing model. In this model, memory is kind of thought to be analogous to a computer. So computer encodes, it stores, and it retrieves. That's the information processing approach to memory. The second model is the parallel distributed processing model. In this model, memory is thought to be distributed over a network of interconnected units. These units work simultaneously in a parallel fashion to process information. The third model is known as the levels of processing approach. In this model, memory is dependent on the degree or depth of mental processing which occurs when material is initially encountered. Fourth, the traditional three-stage memory model, which I'm going to spend quite a bit of time talking about. In this model, memory requires three different stages. So basically, the first stage is the sensory or sensory memory. Then we've got the short-term memory. Then we've got the long-term memory. I'll talk about these at quite some length. But first, here's a bit of evidence for the existence of two memory stores. So the serial position effect. The serial position effect, what is that? Remembering material at the start and at the end of a particular event or time period is much easier than recalling events in the middle. So this is generally known as the primacy and recency effects. So the primacy effect, there's more space available in working memory for elaborative rehearsal during encoding, and the recency effect, items are still in the working memory. So this is the basis for this. The idea is when you start to learn something, you've got a lot of space available to do that learning, so you remember quite a bit at the beginning. Recency effect, your working memory, your short-term memory, events are still in there, information is still in there, so you tend to find it easier to recall those events. So let's go into more detail about studying the information processing models. So we can basically divide this into encoding, storage, and retrieval. So think of memory as encoding information, storing information, and then retrieving that information. So this relates to a computer in some ways. So for example, encoding, that might be the equivalent of typing on a keyboard. Storage, the hard drive on the computer. And retrieval, this is when the information is displayed on, say, a computer monitor. In this information processing model, the processing is sequential. So keyboard, disk, monitor, encoding, storage, retrieval. So let's discuss information processing in more detail. So Atkinson and Schifrin in 1968, they came up with the three-stage model of memory, including sensory memory, short-term memory, and long-term memory. That's how they divided memory. So first of all, you have some sensory inputs. So perhaps you're observing a crowd at a football match. You're observing a crowd. So sensory memory will register all the incoming information. This allows your brain to capture for a very brief moment all the information that's present. So you're looking at a sea of faces in a crowd, and for the briefest of moments, that information is there. It's in your mind. You've got a snapshot of everything. That's the initial sensory input. This leads to your sensory memory. So you have basically sensory memory at this point, a memory of the sensations, a memory in this case of the images that you see. Now, attention to important or novel information takes place unconsciously. So if you're looking at that crowd and there's something unusual going on, I don't know, maybe everyone in the crowd is smiling, but one person looks angry. What will happen now is you will focus on that one individual. You will pay attention. So we pay attention to and therefore encode important or novel stimuli. So in this case, an angry face in a crowd. So initially we got a snapshot of everything That information does not stay in the brain for very long at all. But then something novel appeared in our field of vision. In this case, an angry face. We pay attention. And because we pay attention, this information is retained for longer. It enters our short-term working memory. So we then are aware of this face. Now, if the novel stimuli is particularly important, so this angry person really does leave a strong impression in our memory. Maybe there's something very strange about them. Maybe they do something. Maybe they get up and cause some trouble in the crowd. If this occurs, then the face which was in our short-term working memory, which can stay there for about 30 seconds or so, might then enter our long-term memory. So if we stare at this face for long enough, and we're sufficiently disturbed by it, so it seems important in some way, we might encode it in our long-term memory, and our long-term memory can hold memories for years, for decades even. At which point we can then retrieve the memory perhaps years in the future. So really there are the external events, this sensory input then enters our brains, enters sensory memory. We can then perhaps encode aspects of that stimuli into our working memory, our short-term memory, where it can live for maybe 30 seconds or so. And then if the information or the event is sufficiently strong, leaves a particularly strong impression, it could be encoded into our long-term memory where it could be later retrieved. This is basically Atkinson and Shiffrin's information processing approach to memory. Okay, so there have been modifications to this initial three-stage model. First of all, some information might skip past the first two stages and directly enter the long-term memory automatically. So perhaps we're not consciously aware of some information that is around us, yet it still enters our long-term memory. You don't necessarily need to pay conscious attention to something for it to enter the long-term memory. I'll talk about how that works in a little bit more detail later. So, and also, since we cannot focus on all the sensory information we receive, we select information that's particularly important to us, that leaves an impression, and we actively process that in our working memory. So these two concepts slightly modify this initial three-stage model. Okay, so our working memory. Our short-term memory is now really referred to more commonly as the working memory. It involves conscious active processing of incoming auditory and visual information, and also of information retrieved from the long-term memory. So think of your working memory not being something that just takes information from our surroundings and holds on to it for a while. Think of your working memory as, yes, taking information from around us, but also retrieving information from our long-term memory and putting it all together. So our working memory is a construction based on what's going on around us, and also previous events, previous understandings, previous information. It's all brought together in our working memory. So working memory kind of replaces this concept of a short-term memory. The short-term memory, as previously discussed, just takes information from around us, holds on to it, and then if it's important, moves it onto the long-term memory. But in the working memory model, we bring information from around us, from events that are occurring now, and we combine it with previous experiences and previous memories. That's a working memory. Okay, so encoding, getting the information into our brain in the first place. How do we encode? So some information is automatically processed and encoded, so without really conscious effort. So perhaps you take the same route to work every day. you do that route, take that route enough times, it can just embed itself in your brain without you really being consciously aware of it. You take the route, you take the route again, you take the route again, and it's just automatically processed, automatically embeds itself into your long-term memory. New or unusual information, however, I don't know, such as a phone number, that requires specific attention and effort to encode. So perhaps walking a particular route, you will encode that information automatically, whereas if you're trying to learn a new language, study for some exam, then you need effort and attention for the encoding to take place. So first we'll talk about the automatic processing. So we process a large amount of information effortlessly. It's just automatic. This includes space. So for example, when you read a textbook, you'll automatically encode where on the page the pictures might be, for example, the images. Time. We automatically note particular events that occur on a particular day or at particular times within the day. So time is encoded automatically. We don't have to think, oh, this is occurring in the afternoon, this is occurring in the morning. That information just automatically encodes itself. Frequency. With little effort, you keep track of events that happen to you, the frequency of those events. So space, time and frequency, these are all encoded automatically. Then there's effortful processing. So any novel information that you commit to memory requires a certain amount of effort. So as I've said, learning a new language, studying mathematics, whatever it is, requires actual efforts in order to lead to long-term memories that can be retrieved easily at a later date. So basically, encoding can be divided into effortful encoding and automatic encoding. So how can we influence all of this? Well, rehearsal. Rehearsal is key. So effortful learning requires usually rehearsal. So basically conscious repetition. Ebbinghaus studied rehearsal by using nonsense syllables. So sounds such as yoff or zoz or tuv. These nonsense syllables he would put together and he would have people try to memorize them. He picked nonsense syllables because if these were words that had a meaning to different individuals in the test group, then people would remember those words more easily. He wanted them to be novel, to be completely new. He did not want these words to be able to be linked to previously understood information. Okay, so rehearsal, what did he find? So he basically determined that the more times these nonsense syllables were practiced on the first day of the study, the fewer repetitions were needed to recall them on the next day of the study. So, for example, if we compare time in minutes taken to relearn a list a day after it was initially memorized, compared with the number of repetitions of the list on day one, you get a graph which basically plummets. So basically, if we say time in minutes taken to learn was 20 minutes, then the number of repetitions that is needed might be as little as 8 repetitions. Whereas if the time was just sort of 5, 6, 7 minutes, then the number of repetitions may be 64. So it may take many more repetitions before you actually recall the list clearly. Memory effects. There's a couple of effects that are related to memory. There is the spacing effect and there is the position effect. Spacing effect states that we tend to retain or recall information more accurately when we rehearse it over time. So rehearse it on day 1, day 2, day 3, day 4. We're more likely to recall the information accurately. Then there is the serial position effect. This states that our recollection is more accurate for the first and last items on a list, but not so accurate for the items in the middle of the list. So now what I'm going to do is discuss what we encode. We encode different types of information in slightly different ways. I'll discuss encoding by meaning, encoding by images, and encoding by organization. So different people tend to encode information in different ways. We all use all three of these methods, meaning, images, and organization, but to different extents. Depends on the individual. So first of all, encoding by meaning. This is processing the meaning of verbal information by associating it with information that we already know or imagine. Imagination is key as well. This encoding of meaning is known as semantic encoding, and it tends to result in more accurate recognition when tested at a later date than visual or acoustic encoding. So encoding meaning tends to allow for more accurate memory, a memory that can be retrieved more easily than encoding by just images or sounds. So visual encoding. Visual encoding, basically imagery, mental images. These are a powerful memory aid tool to allow accurate, effortful processing of information, especially when it's actually combined with semantic encoding. So they say a picture is worth 1,000 words, and that can be. It really can be. So a very strong image that has some meaning associated with it will stick in the brain more accurately than just some words, for example. Mnemonics. Now, mnemonics uses this. Mnemonics uses imagery to help the subject to recall information more accurately. Mnemonics is a Greek word. It's derived from the name of the Greek goddess of memory, Mnemosyne. And mnemonics is basically a collection of tools that use imagery to allow individuals to recall information more accurately. Recalling numbers, recording words on their own can be difficult, but if you can associate that information with images using these mnemonic tools, the information will be recalled more accurately. Medical students use mnemonics a great deal. If you check on the internet, you'll find that there are a number of websites for medical mnemonics, lists of images and various phrases that you can visualize in order to remember, for example, the different nerves in the face, or the bones in the body, or the blood vessels, the arteries, the veins in human body. So basically, mnemonics are visual aids to help you to recall information more accurately. Okay, so organizing information also helps with encoding. If you organize information by breaking it down into chunks or into hierarchies, categories and subcategories, then the information can be recalled more accurately. So for example, with chunking, you might organize items into something familiar, into manageable units. For example, if you wanted to recall the number 1666193920011945. Might seem very difficult. You might have to repeat that series of numbers a number of times before it's stuck in your brain. However, if you broke those numbers down into chunks, chunks of digits that have meaning, then they'll be easier to recall. So, for example, the first 4 digits were 1666. 1666, the date of the Great Fire of London. You can visualize the Great Fire of London. It will help you recall those 4 digits, if of course you know when the Great Fire of London was. The next 4 digits were 1939, 1939. Think about World War II, think about when it started. You've got 1939. The next 4 digits, 2001, 2001. A Space Odyssey, the movie, and the book. If you've read it, then you will recall more easily those 4 digits, if you can associate those 4 digits with that book, with that movie. The last 4 digits were 1945, 1945. When World War II ended, well, at least when it ended in Europe. So now what we've done is we've taken the digits 1666193920011945, which is very difficult to recall, and we've broken that down into chunks, and now we just have to recall 1666, 1939, 2001, 1945. 4 chunks, 4 things, 4 items. Recalling 4 items is much more easy than recalling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 items, which is what we would have to do if we recalled each digit separately. Okay, so chunking is used regularly, and another example of chunking might be recalling the Great Lakes: Huron, Ontario, Michigan, Erie, and Superior. Now, you could break that down into the initials HOMES. Holmes. Huron, Ontario, Michigan, Erie, Superior. So the word Holmes is a chunk. You've chunked those lakes together into one word, and it makes it easier to recall those lakes. So chunking is a really useful tool. It's a really useful tool, and many of us chunk information automatically. We do it when we recall phone numbers. You don't tend to try to recall the numbers individually. If you wanted to recall the number 677530, you wouldn't recall 677530. You'd probably recall it in groups of 2 or groups of 3. It would be much easier that way. Okay, so that's chunking. Then we have hierarchy. So if you break down information into general concepts or categories and then subdivide them, you can create a tree, a sort of tree of knowledge, so to speak, to remember information more clearly. So, for example, you might have a heading at the top, minerals, and that might branch out like a family tree into 2 categories, metals and stones. And then maybe metals breaks down into rare, common, and alloys, and stones breaks down into precious and masonry. So this is an example of an hierarchy. Much easier if you visualize this, if you draw it, if you look at it, than just listen to me explaining it. But this kind of hierarchical structure is very, very useful. You can create maps of information, memory maps, so to speak, where you break information down into categories and subcategories. It makes it much easier to recall. Another example might be the human nervous system. So the nervous system would be the top category, the top of the tree, then it would break down like a family tree down into subcategories. So nervous system would break down into the central nervous system and the peripheral nervous system. On one side, the central nervous system would break down into the brain and the spine. Then the peripheral nervous system on the other side would break down into the somatic and the autonomic nervous system. And then the autonomic nervous system would break down into the sympathetic and the parasympathetic nervous system. So if you draw this down as a tree, it's easier to remember than just remembering what each part of the nervous system does all by itself. Okay, so to sort of summarize this in a kind of hierarchical form, encoding can be either automatic or effortful. This can be broken down into meaning, imagery, and organization. Organization can be broken down into chunks or hierarchies. Right, so with that said, moving on, let's now talk about storage, retaining information. So obviously storage is at the heart of memory. It's not just about experiencing an event and holding on to it briefly. Memory, to be useful, requires that we can hold on to information for long periods of time and retrieve it when necessary. So there are three stores of memory, as I've previously discussed: the sensory memory, the working memory or short-term memory, and the long-term memory. So some sort of event will occur, it will register in a sensory memory. Aspects of those events may be encoded into our working memory, and then if those events are of any kind of particular significance, we may then further encode them into our long-term memories, at which point we can maybe retrieve those events at a later time by pulling them out of the long-term memory and placing them back into our working memory. So let's start now by talking about the sensory memory, then we'll move on to working and long-term. So sensory memory. A number of experiments were performed by a guy called Sperling back in 1960 relating to sensory memory. So he basically provided a number of random letters or numbers to subjects, and the exposure time for this information, so perhaps a card containing a number of letters, perhaps 9 letters printed on it, the exposure time for the stimulus was so small that the items couldn't be rehearsed. So you couldn't read them over and over again to try to recall them. The letters were just flashed in front of the individual very, very briefly. This was to ensure that the subjects could not rehearse, practice the information to help them recall them. We wanted to test immediate sensory memory. And when this was done, it was found that this sensory memory is really quite short. We're talking about a 20th of a second, really, 50 milliseconds. So information can be recalled with a certain amount of accuracy for a very, very short period of time when it comes to brief exposures of data, of stimuli. So sensory memory, the longer the delay, the greater the memory loss. So if we compare, for example, the percentage of information of items recognized when you, for example, show a card with a number of letters on it to a participant and then show them some random cards later, or have them write down the information. When we compare the percentage recognized with the delay time, so the delay between showing the letters the first time and asking them to recall them, we see a rapid drop in the percentage of information recalled. So, for example, if you show them the information almost immediately, 0.15 seconds after the initial stimulus, the card with the letters on it, then 80% of that information is recalled accurately. 0.3 seconds results in just 60% of the information being recalled accurately. Half a second goes down to 40% of the information being recalled accurately. And we're down to about 25%, 30% by 1 second. So you show someone a card with some letters on it, and then you ask them to recall those letters. And within just 1 second, we've gone from 80% recall down to 25% recall. So sensory memory is very, very short. But it does vary. Sensory memories, they're not the same for every type of sensory input. So it varies depending on which sense we're talking about. So you might have half a second for iconic memories, meaning information that's coming in through our eyes, vision. Echoic memory, sound, could be 3 to 4 seconds, much longer. Apathic memory, which basically means things like touch, can be about 1 second, a little bit less. So we recall words spoken to us or sounds that we're exposed to slightly longer than we do for images that we see. Okay, so now moving on to working memory. So we're exposed to some information, sensory memory. We pay attention to that information. It may now enter our working memory, our short-term memory. So working memory or short-term memory has a limited capacity, about 7 items, plus or minus 2. So 6 to 9 items, and its duration is short, about 20 seconds. So Sir George Hamilton, he observed that he could accurately remember about 7 beans thrown on the floor. If there were more beans, he guessed. So he came up with this initial idea of 7 items, a storage limit of 7 items, more or less. And that's true. If you're exposed to a 7-digit number, you might be able to hold that in your working memory, in your short-term memory, for a period of time. 9 items, a bit more tricky, There's a limit to it. I should say that human memory is not the best for this. Our cousins, the chimpanzees, have a better working memory than we do. A chimpanzee can recall far more items, more individual items, than a human can. They have a larger working memory, a larger short-term memory. They have a larger sensory memory too. Okay, so capacity. This number 7 plus or minus 2 has been tested repeatedly and confirmed. George Miller, for example, confirmed this number. You can test it for yourself, test your own. So perhaps write down a random digit, a random 10-digit number. Try and recall as many of those digits as you can with just one brief reading. See how you do. You'll probably find you can recall about 7 numbers, 7 digits if you don't chunk, relatively well, plus or minus 2. You might be as low as 6, you might be as high as 9, but you'll probably be somewhere within that region. So chunking can help with that, obviously. If you chunk digits together, you chunk letters together, you can recall them much more accurately. Working memory itself, though, really does not have a long duration. You've really got a maximum of about 30 seconds, maybe 20 seconds is more accurate. So if you can, for example, if patients or subjects are given some random consonants and asked to recall them at different periods, so they get shown a number of random consonants, random letters, random sounds, and they're asked to recall them at different time periods, you will find a rapid decline. So, for example, if you show them the consonants and ask them immediately, so just a second or so later to recall them, they'll probably get up to 80 or 90% of them right. By 3 seconds, they've gone down to 60%. By 9 seconds, they're down to about 20%. And by about 15 or 18 seconds, they've dropped down to as little as 5 to 10%. So most of the contents of the working memory have dissipated within just 20 seconds. So working memory is short, not as short as sensory memory, but still really quite short unless you rehearse, repeat numbers, repeat information over and over again to yourself. That can obviously help. Okay, so we've talked about sensory memory. We've talked about working memory. Now let's talk about long-term memory. So essentially, its capacity is unlimited. Sensory memory has quite a big capacity, but very short duration. Working memory has a fairly small capacity, but a slightly longer duration. Long-term memory has a pretty much unlimited capacity, and unlimited number of items and unlimited time frame for recalling them. You might learn something as a small child and still recall it at the age of 70 or 80 or 90 years old. And it's really impossible to fill your memory. Your brain contains a lot of neurons, 100 billion neurons, and they have many connections with each other. Each neuron can have many connections with other neurons. So you have trillions and trillions of connections in your brain, and it's those connections that make your memories. 70, 80, 90 years on this planet is not enough to fill your memory. Perhaps when we extend longevity, when new medical procedures come into place that allow us to live longer, we will find out that there is a limit to our memory, and perhaps after 200 years, 300 years, 400 years, our memory would fill, but not in a normal or even a long human lifetime. We've got a huge amount of capacity. Not just humans, all animals have a huge capacity. For example, the Clark's nutcracker can locate about 6,000 caches of buried pine seeds during winter and spring, buried in different locations. Squirrels, they can recall quite a lot of locations as well, although not necessarily as accurately. So different animals have different capacities for memory, but we all have a huge capacity. To give you an idea of the sorts of capacity, I'll give you a few. I'll talk about a few particular records that have been achieved by memory experts, a few memory feats. So, for example, the most random digits memorized in 5 minutes is 324 digits. I should say that the humans that can perform such feats, they're not necessarily memory champions inherently. They can use techniques such as mnemonics, the techniques that I've discussed previously, and more elaborate techniques to aid with memory. But even so, 324 digits, random digits in 5 minutes, it's huge. The most cards memorized in 1 hour. So 52 points for every pack correct, 26 points if one mistake. This is how they judge it. Was 1,170 cards. Huge. Binary digits, most binary digits, so binary digit is a 1 or a 0. The most number of random binary digits memorized in 30 minutes when presented in rows of 30 digits to the competitors was 3,705 ones and zeros. Absolutely huge. So we have a massive capacity for memory if we just use it correctly. You may think you've got a poor memory. Maybe naturally your working memory is more towards the 6 than the 9 digits or chunks. Maybe your long-term memory, you find it difficult to memorize information, to retain it and retrieve it accurately over time, but that's just now. I'm not going to talk too much about mnemonics now, but if you study mnemonics, and there's loads of resources out there that will help you with that, you will find that you can improve your recall massively. Absolutely massively. Even things like foreign language vocabulary. So maybe you're learning foreign language vocabulary and it's hard to remember because these are just sounds to you. You know, the sound Kabiza, for example, may not mean anything to you on its own. But if you can turn that sound into something visualizable, something that you can see, then you can recall it more accurately. The word pan might not mean anything to you on its own. Pan, how would you associate pan with the word bread? So you're trying to learn the French word. Pan means the English word bread. How would you do that? Well, think of a frying pan, but the handle of that frying pan is a French breadstick. There you go. Pan, bread, French. One simple image. Mnemonics can be used to help you to retain information that normally would be meaningless and difficult to recall. So if you do have problems with your memory, then perhaps study mnemonics. Mnemonics can really help to improve memory. Okay, so moving on. We've talked about sensory memory, working memory and long-term memory, a little bit about mnemonics. Now let's talk about storing memories in the brain. So Loftus and Loftus, back in 1980, they reviewed a lot of previous research data and showed that via brain stimulation, memories were etched into the brain, and they found that only a handful of brain stimulated patients would report flashbacks. So if you stimulated a particular region of the brain, some patients would then recall a memory, but only a few. Building on, so this kind of implies that there's not one location in each part of your brain for an individual memory. This implied that memories might be more distributed. Using rats, Lashley in 1950 suggested that even after removing sections of the brain, the animals could retain partial memory of say, a maze. So this again suggests that memories are not in one location, they're distributed throughout the brain. So they are distributed throughout the brain. It seems that the visual component of a memory might be stored in the occipital lobe, the back of the brain, where we process vision, perhaps sounds in the temporal lobe at the side, etc., etc. So, and to construct a memory, you're basically storing information in a distributed manner throughout the brain, and when you recall the information, you're basically connecting those different components into one memory, one event, one recollection. Okay, so synaptic changes in the brain. So the brain is made up of cells called neurons. There's different types of neurons, but the neurons in the brain form a network. Each neuron connects with many other neurons. One neuron can stimulate another neuron, can stimulate several other neurons, and other neurons can inhibit neurons. So when a neuron fires, it can stimulate another neuron, or that neuron can be inhibited by another neuron or groups of neurons. So really what's going on in your brain constantly is firing of huge patterns, huge networks of interconnected neurons throughout the brain, distributed. And these are your memories. They are your memories, they are your thoughts. And so basically within the brain, these neurons connect. How do they connect? Well, the gap between one neuron and the next is known as a synapse. Electricity doesn't pass through those synapses, so when one neuron is stimulated, an electrical charge will move along that neuron to the end of the neuron. When it reaches the end, neurotransmitters are released. Neurotransmitters are small molecules. Serotonin, for example, dopamine is another example, acetylcholine. There's a number of neurotransmitters. These neurotransmitters, these small molecules, are released from the end of one neuron. They then bind to the surface of the next neuron and can thereby cause that adjacent neuron to also fire. So this is how information is moved. So we have an electrical signal going along one neuron, and at the end, this causes the release of a neurotransmitter into the gap, the synapse between that neuron and the next neuron, which can then cause the next neuron to fire. But as I said, one neuron is not just connected to one other neuron, not usually. One neuron can be connected to thousands of other neurons. So one neuron firing can stimulate thousands of other neurons in huge patterns of activity, creating memories, creating information. When you recall events, when you memorize something, when you learn something, what will happen is you'll get a new pattern of connections, or new connections between neurons. Neurons that maybe previously were not connected can become connected, or become connected more intricately with neighboring neurons, or neurons in other parts of the brain following stimulation. For example, Kendall and Schwartz in 1982 showed that serotonin release from neurons increased after conditioning. Conditioning being learning of some particular response. You've probably all heard of Pavlov and his dogs, classical conditioning. You ring a bell whenever you feed the dogs. The dogs then learn to associate the bell with food. Then after a number of trials, it gets to the point where you can simply ring a bell and the dog will begin to salivate. This is conditioning. It's a conditioned response. There's different types of conditioning, but conditioning is basically a form of learning, and it's been shown that following conditioning, certain neurons would increase the rate that they released serotonin, a neurotransmitter, which helps these neurons to form an increasing number of connections with each other. Serotonin is really key for learning, and not just learning, even certain mood disorders. So, for example, people with depression have been found to secrete much less serotonin than people that don't suffer from depression. This was the basis for creating the SSRIs, such as Prozac, as a treatment for depression. What they basically do, these SSRIs, which by the way stands for selective serotonin reuptake inhibitors, they prevent serotonin that's been released from one neuron from being broken down and taken back up by the parent neuron. This causes an accumulation of serotonin in the synapses, causing an increase in connectivity between neurons, and if you're lucky, an easing of any symptoms of depression. So serotonin, which is just one neurotransmitter, has been shown to kind of help to cause these neurons to form new patterns, and as a result to help individuals to learn. Okay, so these synaptic changes when one set of neurons connect with another is known as long-term potentiation, LTP. It refers to synaptic enhancement following learning. A lot of research was conducted into this by Lynch, notably back in 2002. He noted that an increase in neurotransmitter levels, or neurotransmitter release, or an increase in the number of receptors for those neurotransmitters, because neurotransmitters have to bind to receptors on the surface of neurons to have an effect. An increase in either the neurotransmitter release rate or the number of receptors on a neuron indicates strengthening of the connection between those two neurons. So if you release more neurotransmitter, or if a neuron creates more receptors for the neurotransmitter, then the connectivity between those two neurons strengthens. What does this mean? Well, in basic terms, it means you learn something, you remember something. The more patterns, the more connectivity between neurons, the stronger a memory becomes, the more you learn a particular task or piece of information. But this can be affected by a number of factors. For example, stress and hormones. So the number of hormones in your body, the types of hormones which can be influenced by such things as stress, will influence your memory. So heightened emotions, whether stress, whether excitement, whether love, whether hate, make for stronger memories. These can sometimes be known as flashbulb memories. These are clear memories of emotionally significant events or moments in an individual's life. So, for example, if something amazing happens, I don't know, your first kiss, for example, assuming your first kiss was amazing, that can leave an indelible memory. You can ask a person at 70, did they recall their first kiss? The first time they held a lover's hand, and they can say in detail, yes, I recall clearly, as if I'm still there now, exactly what it felt like, the sounds, the colours, everything. This is a flashbulb memory. And similarly with negative events, you're in a car crash, you'll recall so much about that car crash. It was such an intense event. You can recall how you felt, you can recall the colours, the sounds, everything. You can relive that experience in technicolor, so to speak. The reason for that is any event that is particularly significant, particularly emotionally significant, I should say, results in the incorporation of the amygdala into the memory process. So you have different parts of your brain involved in memory. One part of the brain is the amygdala, and then there is the cerebral cortex, the outer part of the brain. Now, the cerebral cortex is where memories get encoded. Normally, these memories are encoded in a normal, non-significant way. So you will recall with very little emotion what you did in a particular day. Those memories are encoded throughout your brain, throughout your cerebral cortex. Emotional memories, however, involve the amygdala. The amygdala is a part of our brain, a very small part of our brain, very primitive part of our brain, that associates emotion with memories. So whenever anything particularly stressful occurs, or anything that generates a hugely strong emotion, the amygdala kicks in. It kicks in, triggers the release of adrenaline, cortisol, all of these stress hormones and various other hormones, and they result in the creation of an emotional memory. So yes, we still recall the memory in our cerebral cortex, but we have emotions associated with the memory, and this emotional memory is stored in our amygdala. And if we try to recall such an emotional event, it doesn't just trigger the memories in the cerebral cortex, it also triggers the emotional memories in the amygdala, and therefore we create a vivid, detailed, emotionally rich recollection of the memory, and this is known as a flashbulb memory. And these memories can be very, very intense. An extreme example of which is PTSD, post-traumatic stress disorder. In this condition, a person experiences a particularly stressful event. Maybe they are mugged, maybe they are raped, maybe they're in a car crash, maybe they are in a war zone, whatever. The events can be so strong, resulting in activation of emotion, adrenaline, cortisol, the amygdala, the cerebral cortex. All of these things work together to create a powerful and clear memory. And that memory can be so strong and so emotional that it's hard to forget. It's difficult to forget. People with PTSD can have the memory triggered by anything. They're walking down a street, perhaps they're in a war zone. It's years later. They walk down a street and someone drops something on the floor and there's a crashing sound nearby. They immediately back in that war zone, as if they're there. All the same emotions are triggered. The amygdala is doing the triggering of those emotions. The amygdala kicks in, sets the emotional memory going, causes the release of adrenaline and cortisol. Everything is vivid, everything is bright, everything is sharp. The heart is racing. It's a terrible event. So people with PTSD find it hard to get memories out of their brain. It's the opposite of having a poor memory. It's having a memory that's too strong for certain events. And PTSD can really interfere with people's lives. It can cause anxiety, panic attacks, People can lose their jobs. People can really find it difficult to function in the world if they suffer from PTSD. Luckily, there are certain treatments available now for PTSD. Most of those treatments kind of involve trying to take the emotion out of the memory, to weaken the memory. For example, let's take a simple example. A person has a fear of dogs. Perhaps they have a fear of dogs because as a small child, they were bitten by a dog or barked at by a dog. This triggered the amygdala, which created an emotional memory, very vivid emotional memory associated with a dog, or with dogs generally. And now whenever they see a dog, even a cute little dog, the amygdala kicks in, the heart races, the emotion kicks in. The way to kind of deal with that is to take an individual and expose them to dogs in a controlled and safe manner. So perhaps you start by showing them a very friendly, very small, very nice dog from a distance. You show them it. You tell them that it's safe. You make them realize it's safe. Yes, they'll panic at first, but the more time they spend with this dog in a safe environment, the more their emotions will start to dissipate. They'll start to feel more calm. Then maybe later they will bring them closer to this dog and then closer again. Again, the emotions will be strong at first as the memory is triggered, but then they will soften. Eventually they maybe touch the dog, stroke the dog. What's happening here is each time that they see the dog, it's reawakening this emotional memory that they have associated with dogs. But then, as I said previously, when a memory is activated, it restructures itself. And gradually what's happening here is the memory is becoming less associated with fear, less associated with a traumatic event. It's been associated with the nice little poodle in the room with the psychologist. Gradually the memory weakens, loses its intensity, and eventually a phobia can dissipate completely if the psychotherapy is conducted correctly. So this can work for fear of dogs, fear of spiders, fear of heights, and it can work to an extent with PTSD. It's done a little bit differently then. To treat PTSD, what you will maybe do is have an individual recall the traumatic event in a safe environment. They will recall it in a safe environment. The psychologist will try to calm them down, to try and dispel the emotion from the event. And if this is performed repeatedly, the memory may lose its emotion, lose its strength, lose its vivid colours, and the PTSD may begin to dissipate, especially if this form of therapy is accompanied by the use of certain drugs, for example, propranolol. Propranolol is a drug that is given to treat panic attacks, actually, and to treat high blood pressure. But it also, propranolol also makes it harder to form memories. It interferes with memory formation. So if you take someone with, for example, PTSD, and you give them a big dose of propranolol, and then have them recall the traumatic event, the memory will become vivid again. As I said, the circuit of the memory will open up, become plastic, become pliable. But when it forms itself again at the end of the recollection, and the circuit settles, the memory won't be quite so accurate following exposure to the drug propranolol as it was before. If you do this again and again and again and again, repeat this process, have the patient recall the memory in a safe environment with propranolol in the system, the memory will lose its detail, will lose its vividity, if that's a word, and the person will gradually become okay with that memory, or more okay, and it will interfere less with the day-to-day life. So that's quite an effective treatment for PTSD. What I'd like to do now is differentiate between implicit and explicit memories and how they're stored. So explicit memories are basically memories of facts and experiences that one can consciously recollect and declare. That's an explicit memory. An implicit memory, however, involves learning a particular action while you are basically unaware of how the information came into being. So implicit memories involve learning an action while the individual does not know or declare what she or he knows. So if we take long-term memories, types of long-term memories as a parent category and divide that, then on one side we would have explicit and on the other we would have implicit. So explicit memories, also known as declarative memories, they are memories with conscious recall. They're processed by a part of the brain, a region of the brain known as the hippocampus, which in Greek literally means seahorse. It's a small region of the brain. It's kind of like the shape of a seahorse, although personally I think it looks more like a Chinese dragon than a seahorse. But this region of the brain, the hippocampus, is it's how we process memories, and we actually move them from being short-term to long-term memories. So the hippocampus allows us to store facts, general knowledge, and personal events, experiences that occurred within our lives. So explicit memory is known as declarative memory, involves conscious recall, processed by a structure called the hippocampus in the brain, allows us to store facts, knowledge, and personal experiences. That's explicit memory. On the other side, we have implicit memory, which is also known as procedural memory. This type of memory occurs without any kind of conscious recall. It's processed in a part of our brain known as the cerebellum. Cerebellum is kind of at the back and underneath the brain. This allows us to recall information such as fine motor control of objects. So a good example would be you learn to ride a bike. You get on the bike, you start riding the bike. You don't consciously think, where should I move my left hand? Where should I move my right hand? Where should I place my feet? You don't do that consciously. You do it implicitly. You do it procedurally. You do it subconsciously. Yes, when you learn to ride the bike, you've got to think where your arms are, where your legs are. But once you've learned how to ride it, you do it automatically, because those memories have become implanted in the cerebellum, in that part of your brain, and it's that part of the brain that brings the memories forth and allows you to perform the task. So riding a bike, playing a piano, speaking, walking, all of these things involve the cerebellum. They're all implicit. They're implicit. You don't think when you drive your car, ride your bike, speak, walk. Once you've learned to do these things, it all becomes automatic. Okay, so that's implicit. Classical conditioning is implicit as well. So the Pavlov's dogs, the ringing of the bell, causing the dogs to salivate because the bell has become associated with food. Example of classical conditioning. That again is performed implicitly, not consciously. So once again, types of long-term memories, explicit and implicit. Explicit, also known as declarative, requires conscious control, processed by the hippocampus, involves learning facts and retrieving them, general knowledge, and recalling events. Then we have implicit, procedural memory, without conscious recall. You don't consciously have to recall the events. It's processed by the cerebellum of the brain and allows individuals to perform fine motor control. Talking, walking, riding a bike, playing a piano, driving a car, etc. So let's talk a little bit about how we found out some of this information about how our long-term memory works. So first of all, the hippocampus. As I've said, that literally means seahorse from the Greek. The hippocampus is located in a part of the brain known as the limbic system, and it's directly responsible for processing explicit memories. We found this out basically by studying one individual, an individual known as Henry Mollison. For decades he was simply known as HM. Henry Mollison lost his hippocampus. Well, lost is the wrong word. It was surgically removed when he was quite a young man. Basically, he suffered from quite severe epilepsy, and the surgeon believed that removing his hippocampus might actually cure this condition. At the time, they did not know what the hippocampus did. The surgeon removed the hippocampus from this particular patient, and henceforth the patient, Henry Mollison, suffered from something known as Anterograde Amnesia. This basically means he recalled everything that happened to him before the operation, recalled his childhood, recalled being a young man, all of these things, but he could not form new memories. So Henry Mollison, if you walked into the room, you could introduce yourself to this guy following the operation. You could chat to him. He had a working memory. He had sensory memory. You could have a conversation with him. You could talk to him. But then if you walked out of the room and came back 20 minutes later, he would have no recollection of ever meeting you before. That is what happens when you remove someone's hippocampus. You cannot produce these explicit memories. You cannot store new events, new facts, new information permanently. That's how we learned what the hippocampus did. We also learned a lot more than that from Henry Mollison, because Henry Mollison, following this operation, lived for many decades. I believe he lived to be in his 80s. And for that entire time, he was studied. He was studied by many scientists. There were scientists that worked with him for decades. These scientists, by the way, they worked with him for decades. In many cases, they saw him every day. They would, however, every single day for years and years, when they came into the room, they would have to introduce themselves to Henry, because he would have no recollection of ever meeting them before. That's how strong his anterograde amnesia was. You need a hippocampus to form new memories, and he did not have one. One thing that's quite interesting, though, is he didn't have an explicit memory, but he did have implicit memory. Implicit memory was not affected. As I said, the implicit memory is controlled by a structure in the brain known as the cerebellum. And his cerebellum was unaffected, and this made for some interesting experiments. So, for example, Henry Mollison was taught various procedural tasks over a number of years. He was taught to solve puzzles, for example. He was taught to draw a pattern using a mirror and a pen. So he would see the inverse. He would see the mirror image of, say, a star, and he was asked, using a pen and looking through the mirror, to follow the outline of that star, which is actually very difficult to do if you've never done it before. Your hand wants to move the opposite way to the direction it should move. Now, Henry, when he was first asked to perform this task, made a complete mess of it. The next day, he tried again. He still made a mess of it and had no recollection of ever trying to perform this puzzle before. This continued. After a number of days, a scientist could sit down with Henry Mollison and say, could you try to solve this puzzle? Could you draw the outline of this star through a mirror? And he would say, oh, this sounds difficult, never done it before, it should be interesting. And he would do it perfectly, because his cerebellum had learned the task. His implicit memory had learned the task. So basically, implicit memory is unaffected by damage to the hippocampus. The hippocampus, by the way, can be trained. You might think, oh, I have a terrible memory. I find it hard to learn new events, retain new information. And maybe that's right. Maybe you do have a terrible memory, but it doesn't have to stay that way. Because the interesting thing about the hippocampus is you can exercise it. You can exercise it. You can grow it. You can increase the number of neurons in your hippocampus, and you can increase the strength of the connections between the neurons. You can physically grow your hippocampus like growing a muscle in your body. How do you do this? Well, practice. You study. It's as simple as that. Good example of this. In London, if you're a registered London Hackney taxi cab driver, then you have to perform a test to get your license. And it's a very, very hard test. What you have to do is you have to memorize every street, every roundabout, every turn in the entire London metropolitan area. And London is a big city, and it's an old city, meaning there are lots of streets, lots of small streets, lots of turns, lots of dead ends, lots of streets to memorize. It takes the cabbies about a year or so to memorize this map. They basically just keep looking at maps over and over again, practicing over and over again. And at the end of this practice, they are tested. So, for example, the instructor might say to them, "Okay, you're in Marble Arch. You pick up a fare, and you need to take them to Bond Street." And then the cabbie will have to say, "Okay, I take a left here, I go 1 mile here, I take a right here, down this street, a left here, a right here, a left here, etc., etc." And that's a test, and they are tested over and over again. So, what happens to the taxi driver as he learns these maps? Well, his hippocampus gets bigger. He develops a better memory. Brain scans have been performed on individuals before they started learning, before they started practicing to take this test. The test is known as the knowledge, by the way. And the brains have been tested following, completing and passing the test. And when the brains were analysed before and after, it was found that the hippocampus grew substantially. So your capacity for recall can increase. Your hippocampus can grow. To do that, you need to keep your brain active. You need to study. Keep your brain active and your hippocampus will stay large. So my advice to you, throughout your life, always keep your brain active. Learn a new language. Learn a new skill. Study. You don't have to do it continually, but regularly. Regularly keep your mind active and your hippocampus will stay strong, will stay well wired, will stay large. Your memory will stay reasonably accurate and reasonably clear. I should say that if you suffer from a condition such as Alzheimer's disease, the first structure in your brain to be affected is the hippocampus. That's why people with Alzheimer's disease find it so difficult to retain information. The hippocampus just starts to degenerate. New medicines are being developed to try and address this problem, but at the moment the medicines are not terribly effective. This isn't a podcast episode about Alzheimer's disease, but what I might just quickly say to you is that one recent study or series of studies has determined that the best thing you can do to prevent the onset of Alzheimer's disease is to sleep. Sleep is key. When you sleep, when you go into deep sleep, you kind of rinse out your brain. There's a fluid that bathes your brain called cerebrospinal fluid. You produce it in your brain, it bathes the neurons. When you go to sleep, when you go into deep sleep, your neurons kind of contract a little bit. The synapses expand between neurons, and the liquid, the cerebrospinal fluid, washes out any toxins that have accumulated in your brain during the day. That includes a particular type of protein known as beta amyloid, and another type of protein known as tau. Now, beta amyloid specifically is associated with building up a plaque within the brain that is associated with Alzheimer's disease, and that amyloid plaque builds up during the day and is washed out at night. If you don't get enough sleep, or if you get poor quality sleep, then this amyloid can slowly build up in the brain until it starts damaging the neurons. So the best way to prevent Alzheimer's disease is to get good sleep. 8 hours a night, good quality sleep. You will help to wash this amyloid out of your brain and at least put off the onset of Alzheimer's disease by a few years. So sleep is key. I mean, a good example of, I know this is anecdotal, but it gives you it does help to illustrate how Alzheimer's is linked to lack of sleep. Both Prime Minister Margaret Thatcher and President Ronald Reagan prided themselves on being able to survive with very little sleep, just a couple of hours a night. Both of them, throughout their premierships, had very, very little sleep, and they were proud of this fact. They boasted about it. And both of those individuals later developed Alzheimer's disease. So a word of warning there, get enough sleep. So now let's talk a little bit about retrieving memories, getting the information out. By out, I mean out of the long-term memory and into the working memory. How does this occur? Well, there's different measures of memory. First of all, recognition. This is when a person must identify an item amongst several choices. For example, a multiple choice test requires recognition. If you had a question on a multiple choice test, such as name the capital of Italy, and your choices were A, Brussels, B, Rome, C, London, D, Paris, you might easily recognize the correct answer as being Rome. It stands out. You recognize the correct information. But that's recognition. A different measure of memory is recall itself. In recall, the person must retrieve information using some sort of effort. For example, if you have a sort of test where there is a blank that you need to fill in. For example, the capital of Italy is, and then you have a blank. You don't have any options here. So it's not a matter of recognizing something, it's a matter of recollecting, of actually bringing a memory forward. So these two types of memory are slightly different. And as a university lecturer, I can tell you that students perform differently to a different level, depending on whether I give them a multiple choice test or a test where you have to fill in the gap, so to speak. With recognition obviously being much easier. You immediately will look at an answer in a multiple choice test and you might think, that's definitely wrong, so is that, this doesn't look right, this kind of looks right, and you will then have the right answer. It's an easier way of performing a test. Multiple choice tests are pretty easy compared with fill in the blank tests. In relearning, the individual shows how much time or effort is saved when learning material a second time. So for example, you might present a list of items to a subject and get them to memorize it. So a list of words, for example, and say it takes the participant 10 trials to learn the list on day one, so that they can then just write the list down and they've got it. Now, if you then show the individual the same list a day later, it might take 5 trials to memorize it the second time. So maybe they had to read it 10 times to be able to reproduce it perfectly on day 1. But then if they're exposed to it again on day 2, maybe they just have to look at it 5 more times before they've got it. And perhaps on day 3, day 4, day 5, they will recall the list even easier. Maybe just have to look at it once until eventually they don't need to look at it at all. They've just got it in their head. So relearning is easier than learning from scratch. If you learn something, forget it, then try to learn it again. It will not require as much effort as it did the first time. The way we kind of get our memories back to the surface from our long-term memory into our working memory, this retrieval process is facilitated by retrieval cues. So our memories are held, they're stored in a web of associations. So I've told you that you have networks of neurons throughout your brain, different parts of your brain, all relating to certain memories or certain aspects of memories. These groups of neurons are linked together, which basically means memories are linked together. They are associated like anchors, and these associations help us to retrieve memories. So, for example, perhaps you would hear the word hose, and then the word smoke, and then the word fire, and then the word red. Gradually, these words, which are being activated throughout your brain by different patterns of neurons coming to life, will associate together into a pattern, and that will allow you to retrieve another memory. Perhaps the memory fire truck. You hear a few words, you think, fire truck. So memories associate with each other. You think of one thing, it triggers a second thing, a third thing, a fourth thing, a fifth thing. Memories are linked to each other. They're associated. One aspect of a memory will act as a cue, a retrieval cue, to bring up an entire memory, a complicated scene or an event, by bringing up other associated memories. So to retrieve a particular memory from a huge web of associations, you need to pull on one strand, one piece of the memory, and this will then bring up the other associations. This is known as priming. So, for example, perhaps you will see or hear the word rabbit. This now will activate a bunch of memories in your brain associated with the concept of rabbit. This will prime you for related memories. So, for example, maybe if someone says, following activating the memory of a rabbit, someone then says, spell the word her. Now, if you'd been primed with the word wig, perhaps you would spell the word her, H-A-I-R. However, if you're primed by the image of a rabbit, you may spell the word her, H-A-R-E. This is called priming. So, an event, an image, a sound can prime your brain to then perceive or retrieve further memories in particular patterns. This is known as priming. And priming, by the way, is used by the advertising industry and the marketing industry, and actually by magicians quite often, to manipulate the behavior of customers and of audiences quite effectively. You can get someone to think a certain way, to react a certain way, or to buy a particular product by priming them. This is why when things like soft drinks are advertised, you get that sound of the bubbles in the glass, and you've got condensation on the outside of a glass, and all these images come together to make you think of the taste of the Coke, for example, and of the feeling of being satiated, and it works very, very effectively. And perhaps you'll then go and buy the soft drink in question, or grab a can of it from the refrigerator. Okay, so now let's move on to context effects. Context is important for memory. If you learn something in a particular environment, in a particular situation, then you will recall that thing more easily when you are once again in that situation. So, for example, scuba divers will recall more words underwater whilst diving if they learned the initial list when they were also underwater diving. So you associate. This can be used, by the way, quite effectively when you're studying for exams. So, for example, perhaps when you're revising for a particular exam, you always use a particular pen, you always wear a particular band around your wrist, or you spray yourself with a particular aftershave or perfume. So when you're studying, you do that. Then when you go to the exam, you make sure you are wearing that same band, using that same pen, wearing that same cologne. Make sure you don't wear it in between though. That way, you will sit down at the exam and you will have the same context as you had when you were studying, and will be more likely to recall the information effectively. I mean, a number of studies have confirmed this. It's really context is really key to effectively recalling events and information. In fact, the amount of information that you can recall, if the context is the same as when you actually learned the information initially, you can actually increase recall by up to 20%. So huge amount. This was confirmed in a study, if you want to look up the study yourself, conducted by Golden and Badley back in 1975. Okay, so talking about memory, any conversation about memory really, sooner or later comes to mention the term Deja Vu, which I'm going to do now. Deja Vu. I said that already. Deja Vu, which literally means I've experienced this before. How does it work? Well, it's all down to cues, memory cues. So cues from a situation that you now find yourself in may unconsciously trigger retrieval of earlier similar experiences. So by linking to those memories, those previous memories through association. Patterns of neurons linking to other patterns of neurons. It's all part of context and those context effects. So, for example, a context effect might be, a good example would be Rovey and Collier back in 1993. They studied babies and their reactions to certain stimuli. And they found that after learning to move a particular mobile toy by kicking it in the crib, infants more strongly responded when retested in exactly the same context rather than a different context. So if you put them in a crib that's different, that has got a different colours, different shape to it, different items present, the baby will relearn that kicking the mobile causes it to move, but they won't learn as quickly as if you put them in the same context, the exact same context. They'll relearn it much quicker when the context is the same. So your moods and your memories are all part of context as well. We recall experiences that are consistent with a current mood. This is known as state-dependent memory. If you experienced an event when you were angry, you're more likely to recall it again when you're angry. If you experienced an event or stored a memory when you were feeling very happy, you're more likely to recall that particular event when you were happy again. Good example of this might be if you have an argument with your partner. You're angry, she's angry, you recall a previous argument, you recall something bad that she did previously or he did previously that also made you angry. The previous event was stored when you were angry, and now you're angry again. It all floods back. All the bad things your partner has done come back to you when you are once again angry with them. Whereas when you feel happy with your partner, you recall all the happy events that you did together. So mood is associated with memory. This is known as state-dependent memory. State-dependent memory. Forgetting. Why do you forget? So we've talked about memories themselves, so you actually form these memories, but why do you forget? Why do you fail to retrieve information that you previously could retrieve? There's a number of reasons for this. First of all, poor encoding. If you don't encode the information very well, it's difficult to retrieve it. Poor storage. The memory was not stored in an efficient way, in a way that makes it easy to find. Maybe it wasn't stored very strongly. And retrieval. maybe basically there's a problem with retrieving the memory. So maybe you don't maybe you have a problem with encoding, storage, or maybe it is just retrieval of the memory itself. A good example might be this. Most people have difficulty remembering dreams, at least for very long. There's a number of reasons for this, to do with the way the levels of certain neurotransmitters in your brain at different stages of sleep, but that's only part of it. One key part of why we don't recall our dreams terribly well on average is context. You know, this event occurred to you while you were flying in the sky above a city in your underpants. That's the dream. That's when the event occurred. You wake up, you're not flying in the sky over a city in your underpants. And as a result of that, the memory isn't really associated very strongly with any real event, and it therefore dissipates quite quickly. Doesn't mean the memory's gone. Doesn't mean it's gone. It may be that a year later, I don't know, you see a cartoon on the TV, someone's flying in their underpants, and suddenly you think, oh, that dream, I had a dream about that. It all comes back to you, because now the association has been activated once again. Okay, what about encoding failure? We cannot remember what we don't encode. If you don't encode something, you can't remember it. Remember that there are external events occurring around us all the time, and they will leave an impression in our senses, our sensory memory. But it's a very brief impression. Most of what hits your sensory memory is not stored. It's not. It's only when we, well, depends on the type of memory, remember implicit and explicit, but it's really when we pay attention to something that information will enter our working memory. And when it's in our working memory, then there is the potential for it to be encoded into our long-term memory. So some event occurs, it basically then registers in our sensory memory. Within that event, certain items, certain components we may pay attention to, they may then enter our working memory, and if they are significant enough and we pay enough attention to them, we may then encode them in our long term. But this encoding may sometimes fail if it's not, if enough attention is not given to the object or the event, or there isn't enough emotion associated with it, or it's not associated with any other events or other memories, then retrieving the memory can be difficult as well. There's a term called storage decay, which relates to poor durability of stored memories. Some memories can decay. Ebbinghaus, for example, showed this with what he termed a forgetting curve. So if you visualize a graph, and on that graph on the y-axis you have percentage of a particular list retained when relearning, compared with time in days since learning the list on the x-axis. So percentage of a list retained when learning compared with time in days since learning the list. We see a huge drop as days pass. So day one, a day after learning a list, you may recall, say, 30% of that list. By day 30, maybe you're down to 20% of the list. Right at the beginning, the first day, the day you actually learned it though, you might have recalled 60% of a list. So 60% can rapidly drop after just a day or so to 30%, another couple of days to 20%. So recollection decays over time. Not always, it depends on what you learn and how well you learn it. Different memories will be retained for different periods of time. Very strong, very emotional, very vivid memories can be recalled very clearly or fairly clear for a lifetime. Another study relating to this was conducted by Barrick in 1984. This related to retaining Spanish language vocabulary. So Barrick showed a similar pattern to the previous study I discussed. A previous pattern of forgetting and retaining over a 50-year period. So basically, he analysed a bunch of subjects who had learned Spanish. They'd learned Spanish, and he analysed the recollection of Spanish vocabulary over a period of years, going up to 50 years as it happens. This involved a number of previous participants. And obviously, you get a drop, you get a very similar drop, but if you're learning an entire language, if you're learning huge chunks of vocabulary over several lessons, it takes a while for the vocabulary to fade. It can take a number of years. It will eventually level off, though. So maybe you have 100% recall of the vocabulary within the first year of learning. Maybe that's dropped after 3 years to, say, 30%, and then sort of levels off more or less after that to about 20%. So from about year 5 up to year 50, you might not get much of a change, much more forgetting. If you've managed to retain the information for 3 or 5 years, you tend to retain it for the rest of your life, really. Very similar pattern to the storage decay study performed by Ebbinghaus. Obviously, that was over a period of 30 days, and this study was over 50 years, but you got a similar pattern, a rapid decline in the memories, so a rapid decay in the first chunk of time, which leveled off over preceding time periods. Okay, retrieval failure. Although information is retained in your memory store, it sometimes just cannot be accessed. This generally or colloquially is known as tip of the tongue. Tip of the tongue. It's a retrieval failure. You think, I know this, I'm not quite sure. Maybe you ask someone for a clue, more accurately, a cue. And then suddenly you recall. So maybe someone says to you, I don't know, the hominid that used to inhabit Europe during the Ice Age was what? And you might think, I don't know. Maybe you get a clue. It was Homo. And now you start to think, almost there. And someone says Homo N, and then you think, Neanderthal. I recall. So what's happening here is you've encoded the information, but it's not linked to many other easily accessible memories. So finding that memory is difficult. But then when someone gives you the clue, you stimulate a few neurons in your brain associated with a similar memory that stimulates further memories that will stimulate recollection of the memory that you're trying to recall. You can also have interference of memories by other memories. So one memory can actually interfere with a further memory. For example, learning new information can disrupt retrieval of other information if it's similar. For example, if you've... Okay, so for example, proactive interference might occur if you're trying to study for a Spanish exam, but you've already learned French, or you've learned French quite recently, and the vocabulary can mix. So the previously learned French can interfere with the learning of Spanish. A lot of words are similar. This is kind of proactive interference. Retroactive interference might occur when some new information disrupts retrieval of older information. So here, Spanish that's been learned following learning French might interfere with the recollection of previously known French vocabulary. This would be retroactive interference. So previous knowledge can interfere with future knowledge, or future knowledge can interfere with previous knowledge. Proactive interference, retroactive interference. There are tricks though which can help with this. For example, you can help protect against retroactive interference using sleep. So sleep can prevent retroactive interference, leading to better recall. So when you sleep, your memories are solidified. They're solidified. So long story short, you don't want to be trying to learn two different types of vocabulary on the same day. They're more likely to interfere. If you have sleep in between them, less likely to interfere. When you go to sleep, memories are consolidated. All these things that you learn during the day, they're solidified during sleep. The rubbish, the memories you do not need, are filed away, thrown away, and the information that you do need is stored, is solidified. Sleep helps memory. Sleep helps memory. You probably noticed this if you study for too long in a day. If you study for several hours straight, you get to a point where you just cannot learn new information. You cannot get anything else into your brain. You might just think, "Oh, I'm just tired." Well, you kind of are. When you go to sleep, what will happen is memories that have been hanging around in your brain that are not necessarily required will be thrown away. New memories that you're trying to learn will be solidified, and this sort of increases your capacity to study anew, to study once more. Another way that we forget is known as motivated forgetting. It was Sigmund Freud who came up with this term. This is where people, without conscious effort, revise their own memories. You don't want to remember something a certain way, so you don't. Or you want, conversely, to remember something a certain way, so you do. With motivated forgetting, you choose not to recall certain events. You maybe put some sort of block there. This is known as repression. Repression is a defense mechanism that takes any anxiety-producing memories, things that you don't want to recall, thoughts, feelings, etc., etc., and locks them away, where in theory they can't do any harm. Although this doesn't really work so well with emotional memories, because the amygdala can be triggered without any conscious recollection. Maybe you're terrified of dogs. You don't know why you're terrified of dogs. You never remember having a bad experience with a dog. But it may transpire that as a small child, your parents actually recall that you were harassed by a dog quite badly, and you cried and you're upset. Your amygdala recalls this event. You have an emotional memory, but you don't have a conscious memory. So repression can work in terms of allowing you to block conscious recollection of memories. However, emotional memories can remain. Many phobias are basically memories produced by the amygdala that are not consolidated in the cerebral cortex. You don't have a conscious memory of them. You have an emotional memory of them, which can be triggered by random events. So perhaps you have a fear of having a room of people look at you, or having a small group look at you. You don't know why. It's such a powerful fear that maybe it even happens when you're at, I don't know, having a meal with your family, because they're all around a table and they occasionally look at you and you feel terror. And you wonder, why? This is my family. Why am I scared? But then it may turn out, upon further investigation and analysis, that as a child, there was some event that occurred to you in a similar scenario. So perhaps you were asked to stand up in a classroom at school when you were 5 or 6 and read to the class. And you made a mess of it. And people laughed. And the teacher wasn't sympathetic. You forget that entire event consciously, but your amygdala has an emotional memory that is retained. And that emotional memory can be triggered by similar associations, by being in a room of people, by having people look at you. And suddenly there is anxiety, there is stress. Of course, the treatment for this is exposure therapy. You need to be taught that there is there is no negative to this situation, so you may as well be calm. Easier said than done, requires a lot of practice. Many people suffer from severe anxiety disorders that are very hard to treat, but there are treatments. From meditation, from aversion therapy, from hypnosis to some medications, many therapies. But I'm not going to discuss that in this particular podcast. Maybe I will talk about emotions, anxiety, various psychiatric conditions in another podcast. I will put that on the back burner for now, though. Okay, so summarizing here, why do we forget? Forgetting can occur at any stage of memory. We filter, we change, we lose a lot of information during each stage of memory. Between sensory memory and short-term memory, information may be lost. Between short-term memory, working memory, and long-term memory, more information can be lost. And when we try to retrieve information from our long-term memory and bring it back to our working memory, we may lose information there too. So there's a lot of places where information can be lost, which is why very few people have what you call photographic memories. Or no one has a truly photographic memory, but very few people have a recollection of what they did on every day of their life and every hour of the day. It's very rare to have such strong memories because there's so many places where memories can be lost. And it's good that we don't have that. It's good because you might say, oh, I wish I had a photographic memory. Do you though? Do you really? It's a very good episode of Black Mirror, actually, the TV show, Netflix show, originally on Channel 4 in the UK, that was written and put together by the British guy Charlie Brooker. There's an episode about memory where everyone has a little device implanted into their brain, which allows them to recall everything perfectly. They record everything they see, and it's all perfectly recorded, and they can bring it all back immediately. And in that particular episode, it all falls apart because every little bad thing that someone does to the protagonist can be recalled perfectly, and therefore bitterness builds up. Every bad thing is there, immediately accessible. It's better if we forget the bad things. Remember the good stuff, forget the bad stuff. Accentuate the positive, eliminate the negative, as the old song goes, if I'm remembering it correctly, that is. Okay, so memory construction. So we filter or we input missing pieces into memories as they're constructed and as they're retrieved to basically make a coherent picture. When we think of an event, we like to think of it clearly, and if there are bits missing, our brain fills in the gaps. It fills in the gaps, which is why a lot of memories contain misinformation, inaccurate data, and this can increase over time. This is known as the misinformation effect, incorporating misleading information into your memory of an event, and it can occur very easily. Imagination is key to this. People with greater imaginations can have poor memories in some cases because they fill in the gaps. They fill them in very well. Okay, so for example, maybe you have some eyewitnesses which have to reconstruct memory of an event from something they experienced. So you get them to witness, perhaps you play a video to a bunch of participants of a car crash. Yeah? Two cars crashed together. So imagine two cars, they crash together, perhaps at a medium sort of speed. There's a little bit of debris around the cars. You get the participants to watch this event, and then you ask them some questions afterwards. This is when misinformation can kick in. If you, depending on how you ask the questions, you can alter the memories of the event. For example, you divide the group into two, Group A and Group B. Group A, you ask how fast were the cars going when they hit each other. Group B, you ask the question in a slightly different way. You say, how fast were the cars going when they smashed into each other? So Group A, how fast were the cars going when they hit each other? Group B, how fast were the cars going when they smashed into each other? Now, this alters the memory of the event. Just this simple wording. If you wait a week and then you ask both groups, you ask the groups, was there any broken glass? Group B, the smashed into group, remember, will report more broken glass on average than Group A, where you said hit instead of smashed into. So wording, context, imagination, priming, all of these things come together to cause the formation of memories, and in many cases the memories are formed inaccurately. Amnesia being obviously an extreme version of this. You might completely forget a memory, or forget or recall very, very little of a memory. Now, I also already mentioned that if your hippocampus is removed, you cannot recall any future events. Anterograde amnesia, no future events. You can learn nothing new, no new memories. Well, that is new conscious memories. There's a type of amnesia known as source amnesia. In this type of amnesia, this is where you attribute an event to the wrong source. So maybe there is an event, but you misattribute it. So you kind of think, oh, such a person said this. Actually, no. That was said, but it was said by such a person instead, or in a different place, or at a different time. Oh, remember when you did this? Oh, you did it here, and then. No, I didn't, but I did do it, but it was here and here instead. This is misattribution. So we've always talked about memories and how inaccurate they can be. It leads me to discuss children's eyewitness recall. Now, children have imaginations, and children don't always pay attention quite as in quite as focused a manner as adults do. And this leads to eyewitness recollections of children being quite unreliable, especially if leading questions are posed, which is what happens when trials occur. So if a child has suffered sexual abuse and they're put on a stand in front of a jury, or even if they're interviewed in a private room, the person doing the interviewing, if they word their questions in the wrong way, they can create or instill false memories in the child much more easily than they could in an adult. And this can lead to a lot of problems. This is why interviews with children relating to crimes should be conducted using neutral words, which is easier said than done, especially in cases of sexual abuse or suspected sexual abuse. Okay, so which leads me to talking about memories of abuse. So back, I think I maybe mentioned this already, but there were studies conducted. There were a number of people that were arrested back in the 1990s that were accused of performing satanic rituals with children and abusing them. And much of the evidence for this was retrieved by hypnotizing children or interviewing children using leading questions. And some of the testimonies from these children were unbelievable. I mean, say unbelievable, they were believed at the time, but the things that the children said were done to them by these networks of paedophiles. Yes, paedophilia is real. Yes, child abuse is real. I'm not saying it isn't. It really is. But in the 90s, it seemed there was an epidemic of it. Huge networks. And people were arrested, and people were tried, and people were convicted and put in prison for performing all sorts of satanic rituals on children. And later it was found that many of the memories retrieved from these children and the testimonies given were false. Proof was provided that they were false. So, you need to be very, very careful. Many psychotherapists believe that early childhood sexual abuse can result in repressed memories. So yes, you do need to try and retrieve them. But many other psychologists, and many of the same psychologists, also believe that such memories can be constructed. They can be fake. Not deliberately by the children in many cases, just due to priming and suggestion and all of that kind of thing. For example, Loftus, he performed some research, and this research showed that if false memories are implanted in individuals, they construct and fabricate new elaborate memories. A good example of this. So if you so one study that was conducted, you take a bunch of individuals and you get their parents. So this was done at university, so a bunch of university students. You get the parents to tell the researchers, say, 3 memories that occurred to that individual, to their child, during its childhood, so when it was young. And then what you do is you sit down with the participant, their college student, and you go through these 3 memories. You say, do you remember this? And you tell them this event, and yes, they remember it. You tell them a second, you tell them a third. Then you insert a fake memory. You say, do you recall this event, an event that didn't happen to the child, perhaps being lost in a mall, for example, when they were a child? At first they say, I don't remember that happening. And it's like, oh, okay. Do you not? Your parents said that this happened to you. I don't remember that happening. Anyway, you bring them back a little bit later on another day, and you go through the 4 memories again. You talk about each memory in detail, the first, the second, the third, and this 4th fake memory. And you do it again, and you do it again, and you do it again. As this process continues, in many cases, the individual starts to recall this fake memory. It's like, actually, I do vaguely recall being lost in the mall when I was 6. Maybe it's just a vague recollection at first, but keep going, and eventually, actually, yes, I do. I think I was wearing a red sweater, and then maybe later, and I think the security guard who found me had a moustache, and etc., etc., etc. If this is repeated enough times, the memory can become really elaborate, and this person will recall with absolute detail this event that did not occur to them as a child. So yes, fake memories can be produced. They can be produced even in adults. Suggestion, priming, all of these things can lead to fake memories. Okay, so I think we've covered memory in a reasonable amount of detail. I can only go so deep, unfortunately, in a podcast of this length, but I may return to the subject at a later point, perhaps focusing more on the neuroanatomy of memory. And perhaps I may even put together a podcast purely about mnemonics, but that's for the future. For now, I think we should finish off by discussing a little bit how we might improve our memories. Just very briefly, I've covered this, how memories are formed, how we retrieve memories, why we forget false memories. So it makes sense to finish up by just briefly discussing how one might improve their memory. So first of all, study repeatedly. By this, I mean study, have a break, study again, the same information, have another break, study again. Maybe study on day 1, day 2, then week 1, week 2, month 1, month 2. If you spread it out, it will stick better. Cramming for exams is all very well for that particular exam. If you study really, really hard the day before an exam, you might cram enough information into your memory to pass the exam, but it's probably not going to stick for any kind of long period of time. So if you want to retain the information for long periods of time, then you need to spread it out a little bit. Keep going back to the information and studying it again and again and again. It's more likely to stick that way. Basically, rehearse the material. And think about material even when you're not studying. Don't just think about the material when you're sat at your desk with your books or in front of your computer. When you're walking around, try and bring the information back then. See what you can recall on a day-to-day basis. That rehearsal will help solidify the memories. Make the material meaningful to you. Link it to events, to images, that kind of thing. It's more likely to retain. Memory is more likely to stay in your head if it means something, if it has some kind of link to reality. To help with this, you can use mnemonic devices. You can associate images with words. I've discussed some of this already. You can make up a story relating to the events you're trying to recall. You can chunk things together. You can come up with acronyms. All of this helps you to retrieve information at a later point. You need to activate your retrieval cues, mentally recreate the situation and mood that you were in when you studied, when you learned the information the first time around. It will help you to recall it better. Try and recall events when they're still fresh in your mind, before you encounter any misinformation that might interfere with the formation of the memories. To minimize interference, you need to keep testing your knowledge and rehearse the knowledge and determine what you do not yet know and fill in the gaps with facts, not with misinformation. Finally, I'd just like to say that memory changes throughout your life, but it doesn't necessarily have to become particularly weak with time. It really doesn't. If you keep your brain active, like any muscle in your body, it will stay strong, or it's more likely to stay strong. If you exercise all your life, then at the age of 70, you can be physically fit, physically strong, physically able. If you tend to have a sedentary life, then by the time you get to 50 or 60, things start to wear out. Muscles lose their strength, bones lose their density, you become weaker. And it's the same with the brain. If you do not exercise your memory and exercise your brain, it will become weaker with time. Neurons that are not used, they die. They become weaker and they die. The process is called apoptosis. The cells shrink and they're gone. And it's very hard to create new neurons. It is possible, but it's difficult. It depends on the part of the brain we're talking about. But generally speaking, you need to put some real effort in to create new neurons. Whereas losing the neurons just requires that you put no effort in. Time will destroy the neurons. So you need to keep the brain active if you want to keep it strong. For example, the hippocampus, the part of the brain most directly involved in creating new memories. The hippocampus grows and shrinks all the time. I mentioned the cabbies, the taxi drivers, that have to perform the test known as the knowledge before they can drive London taxi cabs. These guys start off with quite a small hippocampus, but they exercise it and train it, and it grows and their memory improves dramatically. You can do the same. You can do the same. Just keep your mind active. Learn a new language, learn to play the piano, learn to paint. Just keep the brain active and it will be good to you. It will be good to you. Be good to it. It will be good to you. I can speak of this from personal experience. So my original degree, my first degree, was in biomedical science. I worked in biology for a little while, and then I fell into the IT profession. There was a big demand at the time. This is some years ago. I worked in the IT industry for over 10 years. I worked in Singapore, worked in Finland, did quite a bit of traveling. And it was IT, which I suppose is technical, but once I got the hang of the job, it didn't really require much brain power. I knew what I was doing. I wasn't learning anything new, to be honest, for most of the time. Well, at least for the second half of the decade that I was working in IT. After working in IT for some time, I decided to move back into biology. So I came back to the UK and enrolled on a master's degree in genetics, basically, in a form of DNA analysis, more specifically. But yes, it was basically human genetics. I took that master's degree and followed it on with my PhD, which was in cellular pathology and molecular genetics. Now, when I started that master's, in the first trimester, my brain was not working very well. at all. So in the master's program, there were 3 trimesters. Each trimester was divided into about 4 months. The first trimester, I basically did my best, but I came bottom of the class. Out of all of the master's students, I was right bang at the bottom. I started to worry. I thought maybe my brain is deteriorated. I don't have the mind I used to have. I was actually quite concerned. But by the time I got partway through my second trimester, I realised that my brain had changed. It had developed. It had warmed back up again, let's say. And at the end of the second trimester, I came top of the class, top of the group. So you can get it back. You can get it back if you exercise it. I studied hard, it came back, and I've kept my brain active ever since. All the way through the rest of my master's program and all the way through the rest of my PhD. So study, learn, keep your brain active, and it will thank you. Okay, so with that said, I think we're done for today. I really hope you've enjoyed today's podcast. If you would like to know a little bit more about me or my podcast series, then you can visit the website, scienceontheedge.com, or you can follow me on Twitter. My handle is Mark of the D. That's at MARKOFTHE capital D. I'm quite controversial on Twitter, I should warn you. There's a lot of science on there, but there's also a little bit of politics and that kind of thing too. So be warned. Be warned. If you'd like to support my podcast, keep me making them, then feel free to drop a donation my way. You can find a donation link on the scienceontheedge.com website. Okay, that's all for now. Thank you very much, and I look forward to speaking to you again soon. Goodbye.